Dr. Rico here. This is a lecture from my mini course, Robotic Planning and Kinematics. The syllabus and notes are in the description. Okay, 6.3, representing reference frames. We're going to take a look at representing two-dimensional and three-dimensional reference frames in this lecture. We'll look at the two-dimensional ones first because it's easier. Consider two reference frames, sigma naught, the first one, which contains an origin and two basis vectors, or two unit orthogonal vectors that describe a basis for the plane, and sigma 1, which also has its own origin and its own basis vectors in the plane with the same origin. So we're going to set those two origins equal to each other. Because the frames share the same origin, sigma 1 is a rotated version of sigma 0. One can imagine that the rotation is about the direction perpendicular to the figure coming out of the page, or screen, as it were. Let us assume that sigma 1 is obtained by rotating sigma 0 clockwise by an angle theta. So we see here a representation of that, where we have sigma 0 with its x naught, y naught, or x0, y0, and we see sigma 1 with its x1 and y1. The angle that is rotated, that is to say, the angle that sigma 1 is rotated from sigma 0 is shown to be theta. Okay. The array representation in the frame sigma 0 of the basis vector x1 for the frame sigma 1 is given here. So it's x1, that's the subscript 1, it's x1, which specifies which vector it is, okay? And it's represented in frame 0. Remember, x1 is a vector whether or not it has a reference frame, okay? It's a geometric object. If we represent it in a specific reference frame, it picks up that frame as a superscript in our notation. So we say that x1 dotted with x naught, so the amount of x1 in the direction of x naught is the new x component, or the x component of x1 written in the 0 basis. And x1 dot y0 is the y component of x1 in the 0 basis. So, as you can see from a little bit of trigonometry, the x component is going to be cosine theta, and the y component is going to be the amount of x1 in the y direction, which is, of course, just sine of theta, times 1. The hypotenuse is 1 because these are unit length vectors, right? Okay, cosine theta, sine theta. Now, define a 2x2 reference frame rotation matrix representing sigma 1 with respect to sigma 0. So we just represented x1 with respect to sigma 0. Now we're going to represent the entire frame sigma 1 with respect to sigma 0, which requires that we represent not just x1 with respect to sigma 0, but also y1, the other basis vector for the sigma 1 reference frame. So we write this, which tells us that we have a column vector x1 written in the sigma 0 reference frame, and then y1 written in the sigma 0 reference frame. So, expanding that out, this first column is identical to what we wrote above. So this column is what you get when you project y1 onto x naught and y1 onto y naught. So y1 dotted with x naught is going to have this negative value. Okay, it's going to be this direction. And y1 in the direction of y naught is going to be this projection value. Okay, so the trigonometry is fairly easy, fairly straightforward to work out, and we get this matrix in 6.2. For example, if theta is equal to pi over 3, like a 60-degree turn, we easily compute that if we were to express the rotation matrix in the sigma 0 reference frame, this would be the matrix. We simply have plugged in theta equals pi over 3 into this expression and evaluated the trig functions. In summary, we can represent the frame sigma 1 with respect to the frame sigma 0 by either 1, using an angle theta, which is an element of the interval from negative pi to pi, which is just S1, right? Our one-dimensional sphere. Or 2, we can represent it as a rotation matrix, R1, written in the other reference frame, which is 0 in this case, a 2x2 matrix with special properties that will be studied in this chapter. So we're going to look at them a little bit further. 3-dimensional reference frames. Now we've covered 2-dimensional reference frames. Not so bad. We're feeling confident. We're ready for 3D. A fundamental advantage of the rotation matrix representation is that it naturally extends to problems in 3 dimensions. Indeed, let us write down 3-dimensional reference frames and understand 3-dimensional reference frame rotation matrices. So, we've drawn it to get a geometric understanding of what we're doing here. Again, we have reference frames sigma 0 and sigma 1, which have now been redefined just to extend them a little bit further to include a third dimension, z0 and z1. Basis vectors are then picked up by these two frames. And again, we have the same origin as before. The reference frame rotation matrix describing sigma 1 with respect to sigma 0, which is what we did above as well, is the same sort of deal. We're just going to extend it one more column, and we'll write z1 with respect to the sigma 0 reference frame, which just is z1 dotted with x naught, z1 dotted with y naught, and z1 dotted with z naught. So this third column now is here. Also, this third row appears, which is the x1 vector dotted with z naught, the y1 vector dotted with z naught, and the z1 vector dotted with z naught. Okay, that's our new rotation matrix. R1, the rotation matrix that defines the rotation between sigma 1 and sigma 0. The reference frame rotation matrix is also sometimes referred to as the direction cosine matrix. The reason being that each entry is the dot product between unit length direction vectors. And as we all know, the dot product is associated with the cosine of the angle between the vectors. Okay. Changes of reference frame. Since we just studied how to represent sigma 1 as a function of sigma 0, let us also define the reference frame rotation matrix representing sigma 0 with respect to sigma 1. So going the other way, denoted by R0, which is the rotation of 0 written in terms of sigma 1. By looking at the entries in the equation here, this equation here, apologies, the reference didn't come through, one can immediately establish that if you wanted to represent the other of our rotations, or the rotation matrix from one of our reference frames to the other, all we need to do is to transpose. If you want to switch which frame is referenced to the other, all you need to do is transpose your rotation matrix. And we see that because this is a consequence of the fact that the dot product does not depend on the order of the dot product. So A dot B is equal to B dot A. So when we've transposed this, we've effectively just written R0 with respect to R1. So that's a nice result. We continue to consider two frames, sigma 0 and sigma 1, with the same origin. Okay, it's important. Later, we'll look at what happens if we move one relative to the other in terms of origin. Okay, lemma 7.3, coordinate transformation. given a point P and two reference frames, sigma 0 and sigma 1, the arrays P0 and P1 are related through P0 is a point represented in reference frame 0. It is equal to the point represented in reference frame 1 left multiplied by R10. So that reference frame rotation matrix, R10. Here's a little proof on that. First, write the geometric decomposition of the vector that goes from the origin of sigma 0 to the point P. Okay, so that is a vector with respect to x1, y1, and z1. So we do that. We've already done this before for a given point. We can write out what the vector is in terms of any of our basis vector representations, and this is what we've done with x1, y1, and z1. Second, express the left-hand side and the right-hand side with respect to sigma 0. So we've been representing it with respect to sigma 1 up here, but now we're going to represent it with respect to sigma 0. Well, in that case, all we need to do is express the basis vectors x1, y1, and z1 in the new reference frame. So we can transform each of these by saying, okay, x1 represented in the 0 reference frame, y1 represented in the 0 reference frame, z1 represented in the 0 reference frame. All right, so if we pull out those basis vectors and we look at it as being a matrix multiplying a vector, this is seen to be this matrix. These are all column vectors, right? This matrix is just the R10 matrix, and it's just a rotation matrix. So we've proven that property. And this is an important remark, 7.4, to finish off this subsection. Subscript and superscript convention. The role of subscript and superscripts in the equation P0 equals R10, P1 is important. In the right-hand side, the subscript matches the superscript, R sub 1, P super 1, okay? The convention is helpful in remembering correctly how to compose changes of reference frame. And you see this a lot in differential geometry. There's a notation that follows this convention, and it helps do a little bit of error correcting for us, a little error checking. If you're trying to do a rotation and you have the subscript and the superscript clashing, then you probably have a problem, okay? So that's a nice way to remember it. The three basic rotations. Consider two reference frames, again, sigma 0 and sigma 1, with the same origin as before. If the two frames share the same z-axis, that is, if z0 is equal to z1, then there must exist an angle such that x1 and y1 are related to x0 and y0 in this way. So this is just the 2D or the planar rotation that happens, right? It's as if we took the three-dimensional rotation and we said, okay, you can really only rotate about the z-axis, and so the xy plane becomes the rotation that's happening. So you can easily relate x1, x0, and y0, and y1, x0, and y0. This is effectively the transformation that we did in the plane. So that since z1 in the sigma 0 reference frame is 0, 0, 1. So they're the same. R1, 0 is equal to this. So we've transformed all of our axes now, or all of our unit vectors, our basis vectors. And we can illustrate this setup in the figure. So we see that z0 equals z1. We've only rotated in the plane, in the xy plane. Okay. Therefore, this reference frame rotation matrix is a basic rotation about the z-axis that we denote by rotation about the z-axis of the angle theta. That is a counterclockwise rotation about the z-axis consistent with the right-hand rule, as I mentioned before. Similar reasoning can be given for the other two basis vectors. And in summary, the three basic rotations about the three orthogonal axes, x, y, and z, are rotation about x, rotation about y, and rotation about z. This is the notation that we use for these corresponding basic rotations, which is to say a rotation about one of the existing axes. Of course, you can have a rotation about any axis, but these rotations are only about these basic axes, these basis vectors. Okay, given these definitions, some algebraic calculations show that every one of the three matrices satisfy, and we're going to use z here as an example, but it works also for x and y. The rotation of 0 degrees about the axis gives us the identity matrix. So if you were to look up here and you plugged 0 in for theta, you would see cosine theta is 1, cosine 0 is 1, cosine 0 is 1, 1, and these off-diagonal terms, sine of 0 is 0, so and negative 0 is just 0, so we have an identity matrix. It is the same if you look at each of these other matrices as well. Cosine shows up on the diagonal, sine shows up in the off-diagonal, and therefore we get the identity matrix back whenever we rotate 0 degrees, which makes sense, right? If you're going to rotate something 0 degrees, you're not doing anything to it, right? So, like craniosacral massage, I don't know, ignore me. Nothing happens. Okay, so this is, that's the first property. The second property is that if you take the rotation about whatever axis you're talking about, say z, of theta degrees, and you compose it with the rotation about z of phi radians or degrees, the angle phi, then that is equivalent to simply summing the two angles. And there's an exercise that gives you the opportunity to show that or to prove that. Finally, the transpose of the rotation about the axis of theta is equal to the same rotation but negative. Okay, so transposing a rotation is equivalent to changing the sign of the angle that you turn. Okay, which makes sense, right? Because if you were going to go from one reference frame to another, so from say 1 to 2, and you wanted to go back to 1, you would transpose the rotation matrix, right? Going back to 1 is essentially just reversing the angle that you rotated. So it's equivalent to just rotating by some negative angle. All right, so it is good to note that each of these properties has a nice geometric interpretation, and we always like that. Helps our intuition. Their proof is based on simple trigonometric equalities such as these shown in 6.5, and I think you're all familiar with them. The first and second are even and odd function derived, and the others are the sum and difference formulas that you probably have had to do proofs with before. So there is an exercise on this as well. So I encourage you to work through that exercise. All right. I will not be finishing the appendices in the recordings, but I do encourage you to read the appendices. They will be especially helpful for next chapter. And I, in particular, want to encourage you to read 6.5, the theory of groups, before starting the next chapter. And if you need any brush up on matrix theory, then 6.4 is there as well. All right, I'll see you next time.